Linearizing data is basically the process that we use in physics where if we have different graphs, we're always going to want to try to create a graph and put it into what's called slope-intercept form, or a graph that we can use the equation y equals mx plus b. Whether it's a linear relationship or not, we're going to try to what's called linearize the graph or linearize the data so that we can use this, because using this equation is a very simple way that we can gain information. So a classic example of what we might do is in a linear relationship. So let's say we have a lab, and we're doing a lab on Newton's second law, and so we've measured force and acceleration. And what we've done is we've gotten a graph that creates something that looks like this. And so from that, we've gotten the equation y equals mx plus b, right? And we've plugged that into an equation, and we've found that mass equals 12. Right, so what we can do is we can use the understanding of y equals mx plus b and that slope-intercept form of a line to actually understand what does this slope actually tell me. Where if I take what I graphed on my graph, where I plugged in force for my y, m is 12, and x I graphed the acceleration, then I can start to figure out what does each thing represent, because y is force, x is acceleration, and so what does this m or 12 mean? And so if we know Newton's second law of F equals ma, we can see that the mass of the object that we applied a force to must have been 12. And we would know by using some dimensional analysis that it was 12 kilograms. And we can see that from this graph we have a slope that is constant, meaning that we always pushed on the same thing, which makes sense that its mass stayed at a constant value of 12. Now, other things that we can see in terms of using this idea of linearizing data is, let's say we are looking at the idea of refraction. So refraction is the idea that if we have a glass block here and we shine a beam of light into it here at an angle, what we're going to see is we're going to see that light bend, and through the glass it's not going to go in the same direction. And so what we would do is we would measure the angles that they make. And so there's an angle here, we'll call that theta 1. And there's an angle here, and we'll call that theta 2. And using that, we're going to try to figure out the relationship between these two things. Now, if you look at the data, so here we already have example data right here, and we can see that when we graph this, we don't get a nice straight linear relationship. We get this trailing off at the end. And so what we're going to do is try to figure out, okay, how can I manipulate the data so that I can get a nice straight linear relationship? And through experimentation and just pretty much sometimes it's guess and check, we can come up with a linear relationship. Through all of that, what we've been able to figure out is that it's actually a sine relationship. So if we take the sine of theta 1 and the sine of theta 2 and we compare those values, we actually get this really nice linear relationship, right? And so we can then use that equation of the line, which in this case is y equals 0.694x plus b, which if you look, it's a really, really small number. So typically in physics, when we're using this, we're just going to drop that b unless it comes into play as a bigger number. But this value is really close to 0, so we're just going to ignore it for right now and just drop that value. So, okay, well, how would I use that? And so obviously knowing the equation already is very helpful. And so using the idea of index of refraction, there's a relationship where n1 sine theta 1 is going to equal n2 sine theta 2. And so what does this slope tell me? What does this 0.694 tell me? So what I'm going to do is, okay, well, what did I graph on my y? On my y, I graphed sine theta 2 equals m. And then what did I graph on my x? Sine theta 1. Right? And so if I look at that then, okay, well, m then equals 0.694. And if I look then, okay, if I take this equation here and say, well, okay, let's line that up. Basically, I would rewrite this as sine theta 2 equals n1 over n2 sine theta 1. And so basically then I see how this equation here matches this equation here, and so my slope equals n1 over n2, which if I were to know those values, let's say the first n was 1, then I could basically find n2 because I know that this slope here is 0.694. So that's the way that we would take that data that wasn't linear, linearize it, and then we can use that slope to figure out something else. Not a very common relationship that we get in physics. What we're just going to look at right now is just the most common relationships that we get. The first one is called an inverse. So an inverse relationship, we get a graph that looks something like that. And so to linearize, basically, instead of plotting, so this would be y versus x, but to linearize it, what we'd want to do is we'd want to plot y versus 1 over x. So we wouldn't want to plot x, but we'd want to plot 1 over x. Inverse square is a very common one that we see in physics. Coulomb's law, universal gravity, where instead of plotting y over x, and typically you would want to have to plot y versus 1 over x squared. And typically what you would have to do is you will see is people will plot the inverse, 1 over x. They see it's still not linear, so then they're going to try inverse square, and they would square that there. Example of that would be, like I said, universal gravity, where F equals G m over r squared. That's an inverse squared relationship, where we see its force is inversely squared related to r squared. Last examples then would be square root, where square root we're going to have a graph that looks like this. And obviously this was y versus x. Then instead of doing that, to linearize it, we'd want to do y versus x to the 1/2. So we'd want to square root that value. Or if it was an exponential, something that looks like that, kind of parabolic, right? The basic one is instead of y versus x, we'd want to plot y versus x squared. And so those are just the common examples of what you would see when you're linearizing data. And typically what we do is we don't manipulate the graph itself, but we're going to change the data itself. So when you saw those data tables of the Snell's Law one, basically instead of taking sine and sine, or excuse me, theta versus theta, we took sine theta, and then plotted those new values.